Okay, well today I wanted to pick up where we left off, just one little minor detail before moving on to another part of benzene chemistry. Recall we added on different electrophiles to different substituted benzenes. Here we added the OH plus onto nitrobenzene, okay? And remember the nitro group is a deactivator. Over here, I'm going to choose aniline, which is an activator, and look at it reacting with OH plus. What is the major difference between these two reactions? Well, if we looked at the difference using reaction coordinate diagrams, maybe that would be the easiest. Okay. If I did this reaction first and wanted to look at it, how might its reaction coordinate diagram look? Well, again, there's two steps, aren't there? The first step is the slower step, then the sigma complex, and then the second downhill step. Okay? So I'll tell you what we'll do just to make it easier. We'll go ahead and plot both of these reactions on the same plot. Okay? So this one here, we'll label 1, and this one here we'll label 2. Okay? So this one here is that reaction. Now let's compare it to the deactivator reaction where we have the nitro group. What's going to be the difference there? Well, it's going to be a difference in the activation energy. It'll be much higher, won't it? Then when the sigma complex forms, it'll be of higher energy, and then we go down. Okay? So this one here, we can label number 2. Okay? So it's much less reactive because of the deactivator, and the sigma complex will be much less stable because I got an electron withdrawer on there. Okay? Remember, in the sigma complex, we are introducing a positive charge in the ring. So this thing is already electron poor. But now, when I add the electrophile, now the ring becomes doubly electron poor. So this thing is very unstable. It doesn't matter if the positive charge is on there or just in the ring, it's very unstable. Now if the positive charge went there next to the nitro, remember, that really heightened, that escalated the instability. Okay? But I'm just looking at just introducing a positive charge into the ring in general. So that causes the sigma complex to be higher. So that's the difference between the two. Now let's add one more into the mix and call this number 3. And in number 3, I'm just going to take plain benzene that doesn't have any group on it. Where will this react? fall on this graph? Okay. Well, it'll have a higher activation energy than 1, because remember this is electron rich, ready to go, but it won't be as high as 2, which had the deactivator. So it'll be somewhere in between. Okay? So benzene is not as fast as having an activator on there, but it's not as slow as having a deactivator. It's always in between. Okay? So make sure you understand this plot here as it applies to activators and deactivators on the benzene ring. Also, by way of review, let's see if we can predict some more products. But this time, let's have more than one group on the benzene ring. Let's say we had a cyano group and an OH. And we wanted to react with nitric and sulfuric, which again puts what on the ring? A nitro group. Well, where would the nitro group go this time? Well, remember that CN is what? A meta director. So where is meta to CN? Well, there's ortho and there's meta. Okay? So CN is directing here and here. What about the OH? What kind of director is that? That's an ortho-para. Well, where is ortho-para to it? Well, ortho right here. So OH is lining up there, and then para is up there where the CN is. Remember, I can only have one group on a carbon atom in benzene, so I can't add anything there. So here, both of these are directing toward the same position, so that makes my final product very easy to draw. So I put my nitro group in either of the meta spots, as that will give me the same molecule. Okay? So here we learn how two groups can end up pointing toward the same thing. Okay? That makes it very easy to predict what the product is. Okay? It's like everything pointing in one direction and making a decision. That makes it very easy to make that decision. But what happens if I have things going on in my life that's pointing me in different directions about the decision? What do we do about that? Well, we face the same thing with molecules. Let's look at it by another example. Let's look at something like this. Okay. So here I have a CH3 and an OH. They are both what? Ortho-para directors, aren't they? So the CH3 will direct ortho from it, which is right here. Okay? So CH3 is saying I want my nitro group there or there. The OH is saying what? I want the nitro group ortho to me. So it's saying there or there. So the molecule has a decision to make. Is it going to go up where the CH3 wants or where the OH wants? Okay? How do we determine? We determine by this rule here. Okay, the rule is the most powerful activator wins. The most powerful activator wins. Okay? Which is the more powerful activator? Okay? Again, if you look on your chart on page 774, as you go to the left, you get a more and more powerful activator. And in this case, the one more to the left is the OH. Okay? So that means what? The NO2 will add on in one of these two spots. And so we get this product here. Okay? So if I have to make a decision, might makes right. Isn't that right? Well, here, the might is the more powerful activator. And so the NO2 proceeds there. Okay? And that happens even if the group is a deactivator. The activator always wins over the deactivator. Okay, so let's let our next example be this one. Okay, so here, OH, ortho, ortho, and para. So OH is directing in those three spots. Where is the CN directing? Meta, ortho, meta. Okay, and this meta is already taken. So CN is directing over there. We'll here have to make a decision. Again, OH is the most powerful, so we're not even going to consider there. So the NO2, we're going to get a few products this time, aren't we? The NO2 will go up top. It'll come to the side of the OH. And then that's it. When I have to try to choose to put the incoming group between two groups, there's going to be some sterics. And so we'll stay away from that. Okay? So we're going to choose the spots that have the less sterics in them, which would be a mixture of these two products. Okay? So that's how we handle things with more than one group on the benzene ring. Let's look at one more. let's look at this reaction here. Okay. So here we have metaphenylaniline wanting to add on the nitro group. How are we going to handle this one? Well, what we do is we, just like when we named it, we're going to focus in on the middle benzene ring. Okay, so once I figure that out, remember NH2 is a ortho-para director. Okay, and the phenyl ring is ortho, and para. So here everything is adding together, so no decisions have to be made. So I'll stay away from here because of sterics, and so I'll have two products where the nitro is adding on in both spots. Okay, so we'll get the top product. And then we'll have the nitro group add over here. So that's how we do it if we have two benzenes attached together. Just use the internal one and then look at your directors and see where everything goes. Okay? So this concludes our initial set of reactions. And also we've learned how our orthopara and metadirectors work. Okay, and we've also seen how they work in conjunction with activators and deactivator theory. Okay. So now what we're going to do is get back into the chapter and look at the second half of the chapter. The second half of the chapter is going to begin with looking at more reactions of how to put on more and more groups. Okay? So that's what we want to proceed to do, and then we'll come back to this stuff again a little bit later. Okay, so the next group that we want to put on benzene are alkyl groups. And so what we're going to do is look at Friedel Crafts alkylation reactions. Okay, these are very simple reactions. Where what we're going to do is take benzene and this time react with an alkyl group attached to a chlorine and use an acid catalyst once again. And that puts on the alkyl group that we're just symbolizing as R. So this enables us to for example, make toluene, where now my alkyl group is simply a methyl. so now I could put the CH3 on to make toluene. Okay. Let's look at another one. Okay, here be an example how to put on an ethyl group. Okay, so just put the ethyl on the chlorine, and it goes right on the benzene ring. Very easy reaction. So you might be saying these Friedel Crafts are really nice and simple, and indeed they are, but we have a couple of complications with them. Let's look at them. The first complication is that of rearrangements. Okay? Before getting into rearrangements, let's look at the mechanism of the Friedel Crafts alkylation. Let's look at the mechanism over here. Staying with this top reaction, what happens here is the aluminum chloride pulls the chlorine off of the alkyl group and so our electrophile ends up being a carbocation. So benzene ends up attacking it. And we end up getting ethyl benzene and so forth. Okay. I show the mechanism because it involves a carbocation that is our electrophile. And so our first complication is going to be exactly that. So for example, let's proceed to react benzene with 1-chloropropane. Okay? So this 1-chloropropane and aluminum trichloride, when they react, it takes the chlorine off. And we get this carbocation here. So I drew one of these hydrogens sticking up because if you remember back in 241, we learned about carbocation rearrangements, where if I have a hydrogen on a carbon next door to it, remember the hydrogen can migrate over there. Why would the hydrogen want to migrate over? Because when it does so, positive charge would come there. You say, well, why does it want to do that? Well, here the carbocation is primary. Over here, it's secondary. And remember, secondary is more stable. So this regular propyl group doesn't add on. Instead, the benzene will attach to this carbon. And so we would end up with isopropyl benzene. Okay? So the benzene would attach on there, so it adds on the middle carbon instead of the end carbon. Okay? So you would expect propyl benzene, but the carbocation rearrangement adds it on the middle carbon. So this is the first complication you always have to be aware of. Okay? When you see a Friedel Crafts alkylation, before just adding on the alkyl group, check to see if a carbocation rearrangement can occur. Always check that first. Just like when you cross the road. You always look to the right and to the left before you cross. Let's look at the second complication. The second complication is that we cannot have a deactivator on the ring while doing the Friedel Crafts alkylation. Okay? So for example, suppose you wanted to do this reaction. Okay? So here you have the nitro. So wow, okay, I'll just put on this CH3. Nitro is meta, so it should go right on down there. Put the CH3 on, you say, wow, that was easy points. That was an easy problem. But with the easy problem, sometimes they're the trickiest. Here, you would get no reaction. Okay? So that thing doesn't form. The reaction simply doesn't go. Okay? So again, we can't do a Friedel Crafts. The alkyl group will not add on if I have a deactivator on the ring. Okay? So that's the second complication to keep in mind. The reason for that is, again, deactivators make the ring electron poor. The carbocation is not a super strong electrophile. So if the ring's electron poor, that reaction is going to be a very poor reaction because I got a poor electrophile and I got a poor nucleophile from the benzene ring. Okay, so that's the Friedel Crafts alkylation. Let's turn our attention next what's called the Friedel Crafts acylation. Okay? This kind of group here is what's called an acyl group, where I have some kind of alkyl group attached to a carbonyl, and that's what I want to put on the benzene ring. Okay? So for example, suppose I wanted to put on this group on the benzene ring. What I do is simply the same thing as the Friedel Crafts alkylation. I put a chlorine on the carbonyl, and I use my acid catalyst. And my acyl group goes right on. So here is how to make acetophenone. Okay. The mechanism is basically the same as in the Friedel Crafts alkylation, in that what occurs is the AlCl3 pulls off the chlorine, and we get this positive charge on the carbonyl. One of the things about this one is we can draw a resonance so this gives some extra stability to the positive charge. And these two resonance structures make up what's called the acylium ion. Okay? So here, the benzene ring would attack the positive charge on the carbonyl, and that's how it gets added on. Okay? So what kind of group are we putting on? The one with the carbonyl, which is what? A deactivator, and it's also what? A meta-director. Okay? So this is how to put on things such as this. Okay? In doing the Friedel Crafts acylation, there is an extra advantage to the reaction that we want to look at. Okay? And what we will do is look at that extra advantage in our next class.